All right, so let's go into the next term now. So we already talked about alpha being 1 over the coordination number. And so now let's look at omega, or the frequency. So again, this is frequency, omega, sorry about that, omega. And this itself is a product as well. So it is the product of the probability of an atom's having the requisite energy to make a jump and that's nu, the one that looks kind of like a V, and the probability theta that the site adjacent to the diffusing species or entity is available for the jump. So again, let's kind of just recap that again. So this frequency of successful jumps is the product of the probability of an atom having the energy to make the jump and the probability that that site adjacent is actually available. So we can write that as omega equals nu theta. So the first part, and again, this is a product again, so we'll kind of touch on both of these expressions. So let's look at the jump frequency, nu. So this is, again, the probability of it having the requisite energy. So so basically there's two factors, right? An atom has to have the energy to make the jump, and it also has to have a space to go to make that jump. So if something's completely surrounded and there's nowhere to go, even if it has the energy, it doesn't matter, right? So this first factor involves the energy. So if we think about what has to happen, and so let me maybe just draw a very basic structure here. So let's think about this atom. So this is the one that we're thinking about in terms of whether or not it has the energy, right? So this atom or ion, if it's going to jump to this vacant site, right, it has to break the bonds of those things surrounding it, right? So there's a bond here, and there may be one up there, etc., right? Wherever the bonds are, it has to break those bonds from the original site, and it has to squeeze through any sort of site where they're essentially open site, right? Because it's not typically this open, so it have to squeeze through other atoms or ions to get to the new site, which is here. And so again, that process, requires that activation energy delta Hm star, which is the amount of energy that it needs to have, right? And so that was the enthalpy or energy of migration, and so that's related to breaking the bonds and fitting through these tight spaces to get to the next empty site, right? So this energy is typically much higher than the average sorry about my handwriting, it's kind of gone crap right now, but the energy that the thermal energy, or this energy, this delta Hm, is typically much higher than the average thermal energy from temperature, right, that an atom has. So what we see, and let me go on to the next page here, is that only a fraction of the atoms or ions can be expected to have this amount of energy, right? Because it was the average thermal energy, but there's always going to be a small fraction that will have a much higher energy, right? So, but it's only a fraction, and so only a fraction can have this amount of energy based on probability. So only small fraction will be able to make this jump. And so I want to look for a second then at this probability, right? This term that we're talking about, nu, because this is what we need to know, how much energy. And this is governed by Boltzmann's distribution. So this is the scientist that came up with this distribution, right? That's also related to Boltzmann's constant, which we'll see here in a second. And it can be used to describe the fraction of atoms or ions that have the thermal energy. Equal to or greater than delta H m star, our kind of critical value. And so this is, again, a probability. So it's the probability that the energy is greater than delta H m star. And this is equal to a constant multiplied by the exponential over, the exponential inside is negative delta H m star over kt. So this is why you see this exponential over temperature with some type of activation energy, why you see it this form, because it ties back to Boltzmann's distribution. And so Boltzmann's distribution is important not only here in diffusion, but in other fields as well. So wherever you kind of see this, it's coming back to a thermally activated process where only a small fraction of the atoms have the energy of this, right? So basically the fraction here, or the ratio, is the energy required and then the thermal energy, kT. That's what this is kind of showing us. So again, it's a very common form that we see over and over. So we can basically now write our probability, or our frequency that's going to happen, nu, as equal to nu naught times the exponential form that we see over kt. And so this is our now probability or frequency, right? We can think of this in either form, of it having the energy to make that jump based on this number. And so let's think of the nu naught. This is the vibrational frequency, all abbreviated here, of the atoms And so this is on the order of magnitude of 10 to the 13. And that's per second. All right, so I want to look at a couple different scenarios now regarding this expression. So I'll keep this up here at the top, so hopefully that you can see it. All right, so let's look at a couple scenarios here. So if our energy is much greater than the temperature term, the KT term, so this is when temperature is low or the activation energy is large, then our jump frequency becomes very small. Right? That makes sense. That seems to make sense from just practical, what we see. However, if the opposite is true, right? If our activation energy is smaller than the temperature term, so this could happen in one of two ways. Either the temperature is high, or delta HM star is low, right? Then jump frequency becomes much larger. All right, so this covers the first portion of this overall frequency term that we looked at, omega, right? So this is regarding the energy required to make a jump. However, we haven't talked about the term that involves if the site around that atom or ion is actually available. And so that's what we're going to talk about next, is the probability of that site actually being vacant.